I'm Jonathan King, co-founder and chief scientist at Atom Computing, and today I'm going to talk to you about highly coherent qubits and a path towards error correction. First, I just want to give a brief introduction to what atom computing is, if you don't already know. We're a startup focused on neutral atom quantum computing, founded in 2018, with headquarters in Berkeley, California. We've also opened up a second location in Boulder, Colorado. We have satellite offices in North Carolina and Austin. Our goal is to develop neutral atoms trapped in light as a highly scalable, externally accessible platform for quantum computing. We're pursuing gate-based nearest neighbor couplings and focused on achieving capabilities and numbers of qubits that are compatible with known error correction schemes. So this is just a kind of intro slide that summarizes kind of the breadth and importance of where we see quantum computing going in the future. Scientific research, energy, logistics, finance, healthcare, the applications are very broad and far-reaching. But sort of the question is, what does a quantum computer actually need to be in order to access and provide value in all of these different areas? For the sake of illustration, let's consider a particular application. It's really one of the killer apps that people like to point to, and that is molecular simulation for chemistry. So let's motivate this problem a little bit. About 3% of the world's energy is actually spent making fertilizer because people have to grow food and people have to eat. And this is actually a huge, huge energy output. A lot of this energy actually goes into nitrogen fixation, which is one of the steps in the chemical process of making fertilizers. We know that bacteria and plants are much more energy efficient at doing this. There's this enzyme that exists in the roots of some plants called nitrogenase. If we could understand this reaction, we can suppose that we could design a more energy efficient method. And even if we reduce this 3% by a little bit over the entire world, that's actually a huge amount of energy. But it's difficult to simulate. And why is that? Well, here's a picture of this molecule, which is this FeMo-Co, iron molybdenum cofactor. It's a cofactor that works with this nitrogenase enzyme. And the basic idea here is that classical chemistry simulation methods have difficulty simulating molecular structures like this and their properties for technical reasons that I'm not going to go into in too much depth right now. So what does it take to actually tackle this sort of problem in a quantum computer? The number of qubits you fundamentally need is related to the number of electrons or electronic orbitals in the atom, in the molecule. And for that kind of molecule that I just showed you, you would need potentially hundreds of qubits to encode the problem. And I'm going to say this is not necessarily that hard. Quantum computing technologies are already reaching the levels of hundreds of physical qubits. However, if you consider the actual algorithms needed to get good results for this kind of molecule, they need many, many gates. Many steps in the circuit. Actually, I'll click ahead. It's a little difficult to say with high precision exactly how many gates, but people have taken a serious look at estimating how many gates per circuit are needed, and they get numbers that are billions or more. And if we come from the standpoint of understanding that physical error rates in quantum computing gates are honestly harder to make much better than 1 part in 10,000, then you really don't see a pathway to having physical gates on qubits being able to do billions of gates in a row without having an error. So we have this resource that is much easier to get, which is number of qubits, this resource that is much harder to get, which is fidelity, and we really would like to trade one for the other. And so this motivates our goal, which is kind of underlying the thesis of why we care about large-scale, highly scalable qubit platforms. And the goal is large-scale quantum computation with error correction. So now I'm just going to give you a very brief introduction to what error correction is so that the concepts I'm talking about make sense. And this is assuming that you don't have any background in error correction already. So this is kind of a toy model for what the simplest error correction scheme would look like. This is not a sufficient or complete scheme to do practical things, but it illustrates the concepts. So error correction involves encoding quantum information redundantly. For example, a logical qubit 0 can be encoded as 3 zeros on 3 physical qubits, or the 1 qubit can be encoded as 3 ones on 3 physical qubits. The idea being that if any one of these qubits flips, you still have redundant encoding of information. If 0, 0, 0 changes to 1, 0, 0, you still realize that it's closer to the 0 state than it is to the 1 state. So that's redundancy. You can actually measure the errors without measuring the quantum information. It's a little technical here, but basically if you measure the product of the first qubit and the third qubit, whether it's a 0 state or a 0 state or 1 state and a 1 state, there's this idea of measuring, are they in the same state or not? Basically, if there are 0 errors, then every physical qubit should be in the same state. If you find that qubits are in different states, for example, 0, 1, 0, then you know an error has occurred. And you can actually use these measurements to decode what the error is. Either there's no error, in which case they're all in the same state, or one of these measurements has a -1, the other one has a -1, or they both have -1s. And these are the 3 different options that tell you which of the 3 qubits the error has occurred on. So like I said at the start of this slide, useful error correction quotes will have to be much larger, thousands of physical qubits per logical. But this at least illustrates the general point here of how you can actually trade off this resource of having many physical qubits to gain logical qubits that are protected from errors. So what does this look like to a kind of quantum computing scientist? Well, this looks like a circuit. Here are the 3 qubits, Q1, Q0, Q1, and Q2. You have to do gates to actually encode the information of whether or not there are errors on these ancilla qubits. And then you have to read out the errors. These symbols mean measurement. But the idea here is that there's actually steps in this process that are beyond just gates. There's classical processing that comes at the end. Remember on the previous slide, I showed you a decoding table where you actually take the error syndrome and then make a decision about what to do based on it. So there's some classical processing. There's measurement that has to occur in the middle of a circuit because you're actually cycling over this error correction process many times in a practical circuit. And then you eventually have to correct the errors, which could, for example, involve playing a gate to flip a bit that had an error and flipping it back to the correct state. So the point here is that there's a number of things such as measurement, classical processing, and the correction of the errors, which happen in addition to the just regular gates in the circuit. All these things take time. So I'd kind of like to imagine, how does this extra requirement play into what you need out of your qubits in a physical sense? And so that actually leads back into the question of why did we choose to work with neutral atoms in atom computing? And actually more specifically, why did we choose alkaline earth type atoms to make our qubits out of? In this periodic table here, that means it's the second column of the periodic table. So naturally, all atoms are identical. We don't have to manufacture qubits. The qubits exist in their naturally occurring form from nature. And I've highlighted the word stable, and I'll get back to more about that in the coming slides. We can get a large number of qubits. There's a later talk after mine where Krish will talk a little bit more about the specifics of how to actually accomplish this. But for now, I'd just like you to believe me that trapping large numbers of qubits in optical traps is possible. I won't talk as much about how we do this, but the control is wireless because we're using light to position the atoms and also to actuate the gates and also to read out the atoms, read out the qubit states. And we're able to do 2 qubit gates. And Krish will also talk more about that in a later talk. So what really are neutral atom qubits? This sort of cone, or really hourglass shaped, is meant to be zoomed in at the region of highest intensity in a focused laser beam. And this focused laser beam, if it forms an attractive potential, can actually make a single atom be trapped at the point of highest intensity where the beam is focused the most. And this all takes place inside a vacuum chamber. So this is just a very schematic representation of an atom trapped in a laser. You can do many of these in parallel. And you can imagine, so each sort of these hourglass shapes are individually an optical trap, and then the dots in there are individual atoms trapped in each optical trap. There's a little asterisk here, which suggests the actual way we generate these light beams. It's not that we need to buy, I didn't count how many are in here. We don't need to buy dozens or hundreds of off-the-shelf lasers to create these. You can actually take a single source of laser light and then generate these patterns of light using things like spatial light modulators and acousto-optic deflectors. So what we have here is an array of single atoms trapped in optical traps inside a vacuum chamber. So here's where we get into some atomic physics, and my point is to show you the atomic physics, but not expect you to actually walk through it with me. That would be beyond the scope of this talk. But generally, an atom such as strontium-87 can have a fairly complicated internal energy level structure. Basically, there's lots of different angular momentum states, both nuclear spin, electronic orbital and spin, angular momentum. The ground electronic state has this manifold of 10 what we call nuclear spin states. And the definition of a qubit really is just two energy levels that define the bit, it's a binary system, and we need to have the ability to drive gates using the qubit. So I'm not going to dwell on the physics too much here, other than to say, in the ground state of the atom, there are these 10 angular momentum energy levels. We can do a combination of turning on magnetic fields and applying laser beams to do things called Stark shifting, which actually causes energy levels to shift and become isolated from the levels that we care about. There's ways to drive transitions between these two levels that are in the oval here, through two photon transitions, through an intermediate state. But that's kind of the quantum engineering that happens at our company. And the idea is that if we accomplish this well, we can essentially just, for the purposes of this talk, make that complexity go away and think about a 0 state and a 1 state in a qubit, and we can drive transitions between them, which is gates. So like I said, these are nuclear spin levels, and the idea of nuclear spins are actually pretty common in other technologies. If you've ever heard of nuclear magnetic resonance or magnetic resonance imaging, these are actually ways to manipulate and read out nuclear spins, but not in a way that's really useful for quantum computing. But the interesting thing here is that nuclear spins are actually remarkably insensitive to whatever is going on in the environment around them. They have a very weak magnetic coupling to the environment, and as long as you're not shining light on it that's too close to the wavelength of any particular transition, they are very well isolated from the rest of the world. Just as a side note, I used to work in nuclear magnetic resonance, so this kind of thing is familiar to me. Even like when you go into the MRI machine at the hospital, the coherence times of those nuclear spins in your body can be hundreds of milliseconds, which is already kind of a remarkable number for those of you who might be familiar with coherence times for qubits in various other quantum computing platforms. But we don't have, molecules in a body. We have isolated atoms in the vacuum chamber, and that's about as isolated as you could ever get. So they are extremely stable. I'll talk to you a little bit more about that on the next slide. So yeah, let's look at this. There's a couple different ways to characterize lifetimes of two-level systems, quantum systems. And this is a result showing what we call T1. That's a bit of jargon that essentially means if you put a qubit in the 0 state, see how long it takes to decay into the 1 state, or if you put it in the 1 state, see how long it takes to decay into the 0 state. For electronic transitions, usually this might have something to do with spontaneous emission. For various other kinds of systems, it can depend on other physical processes. But what we actually have here is a photograph through a microscope objective of an array of 21 atoms that we actually had in our quantum computer. And we selected the blue and the red ones. That's a color map we added to this image to make it obvious. Some of them we have prepared in the 0 state. Here's a little circuit diagram showing how you actually do that. And some of them we prepare in the 1 state, because that just involves doing an extra flip of the qubit. And then you just wait for some amount of time, and then you read out what state they're in. And we wanted to look at this over many different orders of magnitudes of timescales, just to see the dynamics. Even down here at sub-microsecond timescales. Out here, this would be about 10 seconds at the very end of the plot here. And we can see the 0 state just stayed constant, and the 1 state just stayed constant. And so this is really remarkable. It kind of means the lifetime of the qubit is essentially forever. Of course, it's not truly forever, but it's long enough that it's difficult to measure. And so from the standpoint of practical things we want to do with the qubit, it's essentially forever. Perhaps more important is the coherence time. And this is not just a measurement of how long the 0 state persists relative to the 1 state, but it's if you make a superposition of the 0 state and the 1 state, how long does it retain its phase information? And again, we did a similar sort of measurement here, but we don't just leave it in 1 state, we actually cause it to oscillate, so we can see coherent dynamics, again, happening over a particularly wide range of timescales, again, from kind of the microsecond timescale beyond tens of seconds. And the idea here is that we actually finally did see some decay of the coherence of the qubits, but this timescale is on the order of 40 seconds or beyond 40 seconds. And so, what this can do for us is several things. Of course, fundamental limits on how good fidelities of gates in operation can be are always, once you've solved every other problem, you're always going to hit a fundamental limit of how long the operation takes, how long the gate takes, and the ratio to what the coherence time is. And that's sort of a limit that you can't go beyond. If you're starting with 40 seconds of coherence time, then that really makes the need to go fast, let's say, a less stringent requirement, purely from the standpoint of fidelity. But these applications to error correction described to you on the earlier slides, where you need to do mid-circuit measurement, you need to do classical processing, you need to get information from your qubits into your classical computer. Something needs to happen to decode the error syndrome, and then something needs to happen as a result of that. That also has to happen during the coherence lifetime of your quantum register, of what's going on in your quantum computer. And so having as much coherence time as possible is really important to enabling us to actually scale up to an error-corrected quantum computer that has all the pieces of error correction and does so in a way that it can do it before the atoms lose their information. So this is kind of the last slide with content on it. So you might ask, what about NISQ, noisy intermediate scale quantum? And that's a valid question, because I've talked entirely about error-corrected applications in this talk so far. You can have circuits and gates that have errors in them and still get results out of them. And you can, like, it is known that you can run circuits with errors in them that are difficult or impossible to simulate classically. And so, there are applications that are largely focused in optimization and other sort of heuristic and approximate algorithms. But kind of our vision of a general purpose quantum computer that tackles the most valuable applications really requires this push towards large-scale fault-tolerant error correction. And I'm kind of pointing out a sort of an analyst report here that I think illustrates it fairly well. Right now we're in this regime of, on the order of 100 physical qubits. And, there's these applications that people are interested in trying out. Again, a lot of them have to do with optimization. But the sort of transition of getting logical qubits, where you have hundreds of thousands or more actual physical qubits, is really what pushes you towards these high-value applications that people really, really care a lot about. larger molecule simulation out here is one of them. There's sort of this famous idea of factorization and breaking cryptography. That's the kind of thing that will require very large scale, fault tolerant, error corrected quantum computers. But the final point I really want to make is that in order to enable this, you need a lot of qubits. So you need a scalable platform. Of course, you need sufficiently high fidelities, and you need highly coherent and stable qubits to enable all the steps of the error correction to happen. And with that, I would like to pause and take any questions.